Hello and welcome back to Learning to Program with Go, where in this video we will cover all the operations we can perform with the int and float data types. As you can probably already guess, we can add two numbers that are of the same data type. If I have x set to 1 and y set to 2, we can print out their addition in the print line statement. So x plus y, save and run this, and we get 3 printed out to the console. We can also just assign this to another variable, so we could say z is equal to x plus y, and then go ahead and throw z into this print statement right here. And let's also go ahead and run this, and again we get 3 printed to the console. Now what if we had a number that we needed to continuously modify? So if we only had x here, and let's say that we needed to increment x by 10, well, what we could do is say x equals x plus 10, and then we could print this out. And let's make sure that this all looks good. So another go run, and that produces 11. And then let's say that we wanted to increment it again, and we want to say x plus 2. We can continuously do this, but as you can see, it's a little verbose. We have to say x is going to be assigned to the value of x and then add 10 to it. The shorthand way to go about this is to go ahead and throw this out and say plus equal 10, x plus equal 2 or 1 or whatever it may be. And so this is the same exact thing as doing the x equals x plus 10. So let's go ahead and confirm that this will come out to be 12. Save the file, go and run this, and we get the number 12 printed to the screen. Very similar to doing subtraction. All we have to do is just change this to a minus sign, and then we can keep this as a plus, it doesn't matter, and we can go ahead and save, make sure that everything's running well, and we get -8. So just keep in mind that you can use the shorthand operation of the minus equals, plus equals. You can also combine this with the multiplication, division, and modulo operators too. An even more shorthand way, if you only need to increment by 1, is using the post increment operator. So instead of having to repeat x plus equals 1 a whole bunch of times, we can just do x plus plus. And so let's go ahead and remove those two, so we can see that x starts at 1 and then we increment it by 1, so this will print out 2. Save, go down to the console here, and we get 2. You can do the same thing by doing minus minus, and we can see that when we go ahead and run this, we get 0. Now let's talk about a really important concept called overflow and underflow. And how we're going to demonstrate this is by using a uint8, which means that we are using 8 bits or 1 byte to store a number's value. So if I have num set equal to 0, its bit string in the computer looks like just all zeros. And if I incremented num by 1, this will go ahead and produce the bit string 0000001. And if we were to increment this number again, so we did num plus plus, we're going to get the value 0000010. Whereas when we try to add the 1 in this spot, since we're using binary, we can only do a 0 or a 1 here. The 1 gets carried over to this position, and then a 0 is now taking its spot. If we continue to add 1 to this uint8 or byte, we can end up with bit string 11111111, which is equivalent to 255. So what do you think would happen if we have maxed out our bit string of all ones and we try to add 1 more? Let's go ahead and find out. So we'll go ahead and set num equal to 255. We'll make sure to go ahead and print this out just to prove that it is 255. And then we'll do num plus equals 1. We could also do plus plus, but just to make it explicit, we are only adding 1 to the number. And we'll go ahead and print out num again. So save, run this, and as we can see, the first print statement runs and we get 255, and then we added 1 to that number, and all of a sudden we get back down to 0. Now what happened here? Well, if 255 represents 11111111 and we try to add a 1, we're going to try to add the 1 in this spot, but we have to flip the bit and then carry the 1, so this becomes a 0. Same thing happens here. We carry the 1, try to add 1 in this spot, it becomes a 0, and we continue this pattern until this all just becomes a bunch of zeros, and then you get the 0 number. Conversely, if we have our number set to 0 and then we try to decrement it by 1, so instead we'll do a minus equals 1. We started at 0 and then we decrement it by 1 and we get 255, the maximum value of a uint8. And just in the explanation that I gave up here, we have a bunch of zeros, we try to subtract 1 from each one, and then we end up with a bit string of just all ones. So if you know the bounds of your data type, be very careful on on when you're adding, subtracting, and doing all these other numeric operations on it that you're not going to go under or over the minimum or maximum values of the data type. Many of the operations that we could do with an int are the same with floats. So if I change my num to a float 32 real quick, and then we set num equal to 0, which technically it's a 0.0, we can do num plus plus, go ahead and print that out to the console. And we can do a num minus minus, again, can just print that to the console to make sure that it looks good. And there we go. It goes to 1 and 0. Doesn't have to show any of the decimal points, but if we go ahead and do a num plus equals 1.5, so another float 32, or this gets type converted to a float 32 here, and it's inferred, you can go ahead and print that one out, save, and then we get that decimal showing up that we got a 1.5. We can also do multiplication between two numbers. So if I have x is equal to 2 and y is equal to 3, we can get a result that is equal to x times y, and then print out the result, and we get 6, and the result of integer multiplication ends up being another int. Now, one interesting thing is that we can do sort of an interoperation between different literal data types. If I go into my print statement here, I can do 1 times 1.5. And what happens here is Go does a type inference on 1 and sort of infers that this is actually just a float 32 or float 64, whatever it's treating this 1.5 as, and we'll go ahead and print it to the console. So let's remove these, save, and we'll see that we got a 1.5. Similarly, we can go ahead and do float multiplication, and we get a 5.25 printed out here. And just like we have with addition and subtraction, we can assign multiplication in a shorthand way. So I can do x times equals 10. So this would be x equals x times 10, which will evaluate to 50. So let's replace this print statement and print x, run this, and we get 50. Division gets a little tricky when it comes to integers. If I have x is set to 5, and I'll change this line here to y equals 2, if I did x divided by y, what do you think would be the result? In our math, we know that 5 divided by 2 is 2.5. But if we're working with integers, which are whole numbers, we can only get a whole number back. So let's run this, and we see that we get a 2, even though that we know that the result is 2.5. So no matter what the end result is, whether it be a 2.9 or a 1.8 or a 1.1, there is no rounding that occurs in the number that you get back. The decimal completely gets truncated and you get the integer at the very front. If we were to change these to float values, we can go ahead and do a 5.0 and a 2.0 here, and then go ahead and do the division. We do go ahead and get that 2.5 back. So just be careful when you're working with integers and floats and doing your division if a decimal is critical. If you're new to programming, then the modulo operator will sound unfamiliar to you. The modulo operator purely just takes the remainder of a division result and gives it back to the assignee. If I have x is equal to 5 and y is equal to 2, and we do 5 divided by 2, we know that we get 2 plus 2, but then we have a remainder of 1, right? So we can go ahead and see that result happen. So to use the modulo operator, you use the percent sign, and what we'll see is that we have a remainder of 1 produced. Now you may think, what is the point of using the modulo operator? When will I ever need to have the remainder of some value? Well, commonly it's used to produce if we know a number is even or odd. As you can see, 5 here is odd, and when we divide it by 2 or take the modulo 2, we get a 1. But if we were to change this to 6, 2 evenly goes into 6, and so when we save and run this, we'll get a 0. So that's a quick way to figure out if a number is even or odd. Another common use that it has, especially in particular LeetCode problems, is trimming off digits from an integer number. If I make x 1, 2, 3, 4, 5, 6, and I go ahead and remove y because we don't need it anymore, and I just do a modulo 10 of this, we'll see that 6 gets taken off from this x, or we just get the value 6, but it doesn't actually modify x at all. So save, and we'll see that we get 6 back, because when you go ahead and divide this number by 10, we end up with some remainder of 6. And what you could do here is then go ahead and use integer division and do x divide equal by 10, which will then give us 1, 2, 3, 4, 5. And let's go ahead and print that out just to confirm that. So we can print x. Let's go ahead and run this down here. And we see that when we originally pulled the 6 from line 8, and then we divided by 10, and then we have 1, 2, 3, 4, 5 left over. These are just neat little tricks that you could do with the modulo operator, but it won't be used a ton in your programs. Another odd and uncommon concept used is bit shifting. So let's go back to our example using a uint8. So I have a var x going to be uint8, and if I assign x equal to being 1, its bit string looks like this. So 0, 0, 0, 0, 0, 0, yes, 0, 1. And what if I wanted to shift all of these bits to the left by 1 spot? We can go ahead and do x is equal to x, and we want to shift left, so we use the less than symbols, and we say that we want to move everything over by 1 spot. So this will go ahead and produce 0, 0, 0, and then 0, 0, 1, 0, which is representing 2 in decimal form. So let's go ahead, print x out to the screen here when it's 1, and then after we go ahead and bit shift to the left 1 spot. And since this represents 2, we will see 2 from line 13. So save, go run, and we can see that we initialized it to 1, and then after bit shifting, we got a 2. Now, what if we wanted to bit shift to the right 1 spot? Well, this 1 will go to the right, but there is no place for the right to go to, and so we just get a 0. There is no wrapping of the bits or anything. We just lose that bit. So if I save and run this again, we'll see that we started at a 1, bit shifted to the right, and we got a 0. You don't always have to bit shift to the left or right 1. We can do 2, and so we'll go up a power of 2 this time. So let's go ahead and run this real quick, and we'll see that we went from 1 and then all the way to 4, because now the bit string has moved to becoming this. Commonly, bit shifting is used for multiplying or dividing by powers of 2, or unpacking data. In some languages, it's common that when performing an operation on 2 different numeric types, type promotion is utilized where the smaller bit data type is promoted to the larger one, so no data is lost. But in Go, it does not support automatic type promotion, and it requires that explicit type conversion happens when these operations occur. As we can see here, we have x is an int and y is a float 64. It's not simple to just do x plus y. As you can see, we're getting a compiler error right here. So what we must do is explicitly type convert one of these values. So as we can see, x is an int, so we can just go ahead and convert that to a float 64 to make this work. And how we do that is just do float 64, so you give the data type and then you wrap it in parentheses. And as you can see, we're not having any kind of error here anymore. So if we run this, we get the 1 plus 2 operation that we wanted. But at the end of the day, this expression right here produced a float 64. We can go the other way and not type convert x here, and we can type convert y into an int. So it just truncated off the decimal of y that was invisibly here. This is no longer seen. And then when we do this expression, it produces an integer. All right, if you made it to the end of this video, then you learned quite a lot. All the numeric operations that we have with ints and floats, bit shifting, type conversion, and modulo. So if you made it this far, then please consider liking and subscribing, and I'll see you in the next one.